very much. The recording is now in progress, and we begin this section on investigation, monitoring, and analysis with two invited talks. With the first talk that will be given by Matteo Berti, who is professor in the Department of Biological, Geological, and Environmental Sciences at the University in Bologna here in Italy. Matteo has done research on a really broad spectrum of topics covering landslides of different types and in different settings, from debris flow mapping and monitoring to rainfall thresholds for early warning systems to earth flows, complex and compound failures. And today he will talk about the complex dynamic of active earth flows, a field on which he is a truly international expert, in my opinion. And it will leverage on monitoring data collected over many years in a number of earth flows in northern Italian Apennines. So Matteo, the floor is all yours.
Okay, thank you, Fausto. Okay, let's do that. Okay. Okay, can you see my screen, right?
Yes, you can go.
Okay, I move this, I take the pointer, and I'm ready. Okay, thank you, Fausto, and good morning, everyone. In my speech, I'm going to talk about earth flows, a type of landslide which is very common in all the Mediterranean area, and whose dynamic is, at least in my view, still poorly understood. And the talk will be in three parts. First, we introduce the problem. Then we will discuss the key moments in the life of an earth flow, so the dormant stage, the reactivation stage, pointing out the open problems related to the solid to fluid transition. And finally, I show you the case of the Montevecchio flow, a landslide that recently occurred in our study area and that allowed us to investigate the complex behavior of these landslides. So, okay, let's start with the definition of earth flow. In the literature, there is a general consensus agreement on the definition of earth flow. According to Cruden and Vars, earth flows are slow-moving landslides of the flow type common in plastic, clay, or weathered clay-bearing rocks. And more recently, Anger and co-authors in their new classification defined earth flows as rapid or slower intermittent flow-like movements of plastic clay earth. And these two definitions are actually quite similar and contain several common keywords: plastic clay soils, flow-like, slow-moving, and periodic activity. And these definitions well apply in our study area, the Emilia, which is the Emilia-Romagna region in northern Italy, where earth flows are really the most common type of landslides in the clay units. And clay units, here shown in green with the green color, cover about 35% of the mountain territory in our region. And in Emilia-Romagna, the clay units mostly consist of, let's say, two formations. We have very old Cretaceous clay shales with a laminated texture and young over-consolidated fissure clays. And the weathering of these two clay rocks create thick covers of clay soils on the slopes. And despite the different age and the different geological histories, the geotechnical properties of the soils produced by these two parent rocks are quite similar to the hand. They can be classified as silty clay of medium to low plasticity, but with a relatively low critical state and residual friction angle. And so it's the combined effect of this weak soil, the tectonic uplift, which is about 1 to 3 millimeters per year in this sector of the northern Apennines, and of course rainfall, that makes these clay slopes really prone to landsliding. And the density of the landslides in the Emilia-Romagna region is really quite impressive. And the local geological survey mapped more than 70,000 landslides in the regional territory. More than 50% of these landslides were classified as active or, let's say, recent. And in particular, in the clay units, landslide deposits cover more than 25% of the area. And in this closer view, you can see the density of this landslide. Every single polygon you see here is an earth flow deposit. The red ones are the active earth flow, the blue ones are the dormant earth flow. And you know that earth flows are known as slow-moving landslides. But despite their low velocity, these landslides are of concern to local authorities, but not only in the Emilia-Romagna region, all over the world where these landslides are present. And there are at least two main reasons why earth flows are important natural hazards. Well, the first reason that earth flows can mobilize millions of cubic meters of soil, causing severe damages when they reactivate. For example, this is the Cornillo landslide, which occurred in 1996 in the Parma province with a volume of about 100 millions of cubic meters. Well, this landslide destroyed a factory located here, producing the famous Parma ham, just as an example. So in these communities is to say, earth flows can really have a dramatic economic impact. And also second, earth flows strongly interact with the stream network, delivering a large amount of sediments and generating, in case of damming, a relevant hydraulic risk. So in both cases, the hazard related to these landslides is controlled by their complex dynamics. I mean, in particular, the temporal change of velocity and also the temporal change of the moving mass. So let's see the typical style of movement of earth flows and the open issues related to their mechanical behavior. Here's a conceptual chart showing the typical pulsing or intermittent behavior of the earth flows. It's well known, as you know, that these landslides are characterized by long period of dormancy, interrupted by periodic reactivations. And during the reactivation, the velocity can reach value in the order of meter per day or meter per hours, but for a short period of time, let's say a few days generally. Then the landslide slows down and falls asleep. And during the long dormancy stage, which may last for years, tens of years, or even centuries, the earth flow moves with a typical velocity in the order of several millimeters or centimeters per year. And during this long dormancy stage, the landslide moves generally like a rigid block, sliding along a well-defined slip surface, as you can see, for example, in these dormant landslides in our study area. You see the landslide moves very slowly as a coherent block. So in the literature, there is an agreement on this point. During the dormant stage, earth flow essentially behave like plastic solids. The problem, however, is what happened during the reactivation, so the stage of rapid movement. In general, a reactivation starts with an initial slide located in the main scarp or in the upper part of the deposits. And these initial slides create an undrained loading, which may lead to the mobilization of the existing landslide deposits. And the failure then propagates downslope along the channel, eventually reaching the toe. And the main open question deals with the propagation stage, so with the mechanical behavior of the airflow along the flow channel. According to several authors, earth flows behave like a solid. They look like flow, say these authors, but the internal disturbance is limited and sliding remains the dominant mode of movement. So according to these views, earth flows are, let's say, fake flows. Instead, other researchers, on the contrary, say that earth flows really behave like fluids flowing with continuous internal deformation. And for example, Kiefer and Johnson say that sometimes earth flows are so soft not to support a person's weight. So this issue is still discussed in the literature. And probably both cases are possible. I've seen earth flows moving like solids with a series of, let's say, successive slides. And other really moving like fluids, depending on the morphological and lithological condition. But for sure, this is still an open question. And it's not just a scientific question. It's a practical one. Let me show an example to clarify this point. This is an earthflow that occurred 2 years ago, not far from Bologna. It's a reactivation, again, of an old landslide. The initial slide was here in the upper part. Then the failure propagated downslope and reached the river, the Reno River, in about 10 hours. This landslide caused significant damages, destroying the power lines here, 3 houses, the main road, and threatening the railway, which is located here on the opposite slope. However, the main concern at the time was the hydraulic risk related to a possible damming of the river. As you can see, there is a village here, immediately downstream the landslide location. So luckily, in this case, the earthflow did not transform into a fluid. The material remained in a plastic state. And so it was possible, as you can see in this picture, for the local authorities to excavate the material and to avoid the damming of the river. But the situation would have been far worse with a fluid earthflow, because in this case, both the velocity and the mobility increases. And also carrying on emergency work is much more difficult, because generally the slope cannot be accessed in the first weeks after the reactivation. So the overall risk is much higher with a fluid earthflow. So therefore, in my view, it's important to establish whether or not an earthflow can transform into a fluid in order to predict its velocity and mobility. So in the last years, we have studied a number of landslides in our region, but the one I'm going to show you now, the Montevecchio earthflow, is, I think, of particular interest, because this earthflow turned into a fluid. And we had the opportunity to collect some field data that describe, that document this behavior. The Montevecchio landslide is located in the eastern part of the region. We are not far from the city of Cesena, and this is a general view of the area. You see the typical hilly landscape of the Romagna mountains. All the slopes here are made of young Pliocenic clay. This is the area before the landslides, and this is after the last reactivation that occurred on the 1st of February 2014. If I go back and forth, you can appreciate the retrogression of this source area here. A few pictures of the landslide. This is the source area. The initial slide was translational here, not rotational, because the movement occurred along a bedding plane at the contact between the clay and a thin sandy layer. This is a central reach of the channel looking downslope. The width of the channel is about 40 meters. And this is the toe of the landslide that endangers several houses. These houses were damaged, and the people, of course, was evacuated, but they were not destroyed by the landslide, because the advancing material was continuously excavated and removed. In about 1 year, local authorities spent, I think, more than €500,000 to save these houses. Anyway, we surveyed the landslide soon after the events, and we found clear evidence of a fluid behavior. There were large areas with a soft material with a very high water content. Flow structures were clearly visible along the channel. I mean, arched, pressure ridges, lateral levees, the same structure you can see, for example, in a viscous lava flow. And also, I remember we could easily put a steel tube 2 meters long into the landslide material without any effort with using our hand. And also the velocity was pretty high, in the order of 8 to 10 meters per hour, according to some witness here. So this landslide looks suitable for studying the solid to fluid transition that occurred during a rapid stage of movement. However, as you can imagine, investigating this phenomenon is difficult, mostly because the surface of the landslide cannot be accessed to drill boreholes, to collect samples, and so on. It's also somewhat dangerous, as you can see in this picture. This is Lara, our PhD student. So therefore, in these cases, we cannot rely on the usual geotechnical investigations in situ and the laboratory tests. So we tried to characterize the landslide using a geophysical approach. And we followed here the brilliant idea proposed by Mansand, Dennis Youngsman, and the other co-authors that used surface wave velocity as an indicator of material fluidization. Their idea is actually very simple. In a fluid, the shear velocity is 0. So if the earth flow material fluidize, the seismic velocity should drop to very low values. But of course, measuring the seismic velocity in a rapid moving landslide, earth flow is almost impossible. So our, let's say, contribution, our idea was that we can maybe infer, we can deduce what happened during the rapid motion, measuring the change, the variation of seismic velocity after the reactivation, while the earth flow is decelerating. And this approach is shown this conceptual chart. So you have time here, and this is the seismic velocity. Let's assume that you have the earth flow reactivates here at a certain time. After a while, as soon as possible, I mean a few days later, we go to the field to measure the seismic velocity inside the landslide mass. And then we repeat the measurements over time. If the shear velocity is very low and increases with time, it means that the material underwent a change in stiffness during the rapid motion. And if this difference is significant, it probably indicates that a phase change occurred. Okay, at the contrary, if the shear velocity, let's say, relatively high, and more importantly, is constant, doesn't change with time, we can maybe say that the movement was rigid plastic. So this is the simple idea. So these slides show how we collected the data. First, we performed periodic geophysical MASW-REM surveys, both inside and outside the landslide, to measure the seismic velocity of the landslide material. Second, we installed a monitoring system to have a nearly continuous measurement of seismic velocity with time. The system consisted of 4 geophones, 1 rain gauge, 1 time-lapse camera, and 2 piezometers equipped with pressure transducers. And then we installed 3 GPS stations to measure the landslide displacement. And here we'll focus on this is the monitoring system, the location, the monitoring system, and these are the 3 GPS stations. Saying that here we'll focus on the periodic geophysical surveys, which provided the most significant data for this talk, I mean, for our purpose. So MASW-REM is our standard technique, so I don't want to go into the details. I just want to point out the field setup we used: 6 geophones, 4.5 earth with a spacing of 2 meters in order to reach an investigation depth of 12 meters. The thickness of the landslides, the average thickness is about 10 meters here. And then we recorded 5 MINUs in active mode, so the MASW, and 5 in passive mode using the seismic ambient noise, so the REMI. And the results of these surveys is a dispersion curve, which is a plot of seismic velocity versus frequency. The dispersion curves can be then modeled, you know, to obtain the profile of wave velocity of the soil with depth. Because before showing the result, however, let me point out the history of the events at Montevecchio, because it is useful to understand the measurements. As I told you, the first reactivation was in February 2014. Then in the next 2 months, there were several partial reactivations. The last occurred in April 2014. In May, we installed the monitoring system and we started our periodic survey. Then, during the summer and the fall 2014, the landslide slowed down and we carried out all our works, our measurements. However, the winter was pretty wet with a lot of rain and snow. And so in winter and spring 2015, this landslide reactivated 3 more times. And after each reactivation, we reinstall the monitoring system. And finally, after the last reactivation in June, actually 2015, the landslide really stopped, and now is several remedial works were carried on, and now is in a dormant stage. Here are just a few pictures of the monitoring system before and after a reactivation, just to point out that monitoring an active earthflow is, let's say, hard work. Okay, let's go to the results. In this chart, you see the results of the periodic geophysical survey. Each plot shows the seismic velocity on the horizontal axis and the depth on the vertical axis. And different colors indicate measurements performed at different times after a reactivation. For example, this red line was measured 10 days after this reactivation. But of course, the wave velocity, the surface wave velocity, increases with depth as usual. But the important result here is that seismic velocity also increases with time, as you can see, as the earthflow decelerates. And we observe the same behavior in all the sections inside the landslides. While, as expected, outside the landslide, the velocity doesn't change with time, it remains constant. In this chart, summarize the previous data. In this axis, there is the time after the reactivation, and here is the seismic wave velocity at a reference depth of 2 meters. And as you can see, seismic velocity is very low soon after the reactivation, then it increases with time. The corresponding small strain shear modulus, G0, is very low soon after, shortly after the failure, few megapascal, and rises to up to about 20 megapascal as the earthflow decelerates. Outside the landslide, shear velocity remains constant. So these data suggest, as is written here, that the material probably underwent a significant change in stiffness during the rapid motion. And well, also a clear evidence of a fluid behavior is provided also by the distribution of the displacement velocity during a stage of rapid motion. So let me show you the video recording during the last reactivation. I take the pointer, sorry, okay, turned off the pointer so I can control the video. Okay. Okay, so, okay, here we are. I go back again. We are at the beginning of May 2015, 3 weeks before the last reactivation. And well, as you can see, the surface of the earthflow is full with cracks and open fissures. And now the landslide is moving at a very low velocity, a few centimeters per day. So you cannot see probably this just looking at the video. Well, now in a few seconds, rainfall will arrive. At the 21st of May, rainfall with of about 50 millimeters occurred. And then, as you will see, the rainwater will quickly infiltrate into the ground despite the low conductivity of the material. Just, okay, this is the rainfall. The water disappears, as you can see. And then a few hours later, the landslide accelerates. Apparently now it's slowed down, but then it rains again. And this time the earthflow completely goes. I show you again this critical stage. Just pay attention to the velocity of the landslide. The velocity is much higher on the center of the earthflow and much lower toward the edge. So, sorry. Okay, so this is this behavior is typical of a viscous flow, which has the maximum velocity in the center and zero velocity at the boundary. Of course, is not what we expect for the sliding of a rigid block. Okay, so this is another indication of a flow-like behavior. So making the point, at the Montevecchio, we measured a remarkable change of seismic velocity with time, which indicates a strong variation of soil stiffness. Okay, but the question is this trend significant in terms of change in porosity, water content, or liquidity index? I mean, does the data indicate that a phase change occurred? This is the question. But answering this question is really difficult. And the only possibility we have is to estimate the soil properties from the geophysical data. Although, as you know, these kind of estimates are really uncertain. Anyway, we performed such an analysis using different empirical equations, trying to estimate the liquidity index of the airflow from the geophysical measurements, and also trying to account for the uncertainty related to these empirical equations. Okay, a detailed description of this analysis is provided in the paper that we have prepared for this conference, and which is now under review and hopefully will be published in Engineering Geology. So I will skip, of course, the description of the methodology, and I jump to the result, which is my last slide. In general, all the empirical formulas indicate a significant drop of liquidity index over time after the reactivation. In particular, method C, which is based on the estimation of the void ratio of the earthflow material from the seismic velocity, showed that shortly after a surge, the material is really soft with an extremely high water content, apparently above the liquid limit. And as time passes, the water content progressively decreases toward the plastic limit, and the soil consolidates under its own weight. So these results agree with our field evidences. Therefore, we can say that at least in the specific case of Montevecchio, I don't want to generalize, the airflow turned into a fluid during the rapid motion. But of course, much more the data are needed, must be collected in the field, I think, different geological and geomorphological setting in order to understand in which cases rapid surging of airflow is followed by softening and fluidization, as in Montevecchio, and when instead it occurs by shearing along boundary shear surfaces. So these are my conclusions. Several airflow can really turn into a viscous fluid, other primarily moved by sliding. In the case of fluid airflows, we measured a dramatic loss of shear stiffness and a remarkable increase of water content during rapid movement. We believe that geophysical measurements can provide relevant data to investigate this process, but more importantly, this process is important for hazard assessment, and I really think that it should be better understood. We should really understand the physics behind this process, the physical processes controlling this solid to fluid transition that sometimes occurs in these landslides. So thank you for your attention. You can look at these two papers if you want to have more details on this kind of study. Thank you very much.
Thank you, Professor Berti, for an interesting presentation. And now we have to move to the second invited lecture, but after 10 minutes of break. So see you at 10:30 at second invited lecture.